crucial pieces. And I thought, okay, well, the only other piece I don't understand is like these blob of bytes that has no references to it in IDA, and IDA can't fucking figure out what it is. And I looked at this and was like, okay, I need to look into this. So I decided to look at this blob of code. And I saw this. This is the blob of code that's like repeated a whole bunch of times, right? So how many of you like, this is like stand out to any of you guys? Yeah, so this is like, so I was like, oh man, this code looks very, very familiar. So you recognize the E8 followed by a whole bunch of zeros, and of course I recognize the C3. So I was like, okay, all right, well, thought process again. These bytes are stored, stood out to me because three reasons. One, IDA didn't properly analyze them. Two, they had no obvious cross-references to them. And three, they had reminded me of shellcode, right, just from the byte pattern. So I had another thought experiment. I said, okay, well, if these bytes are shellcode, then they have to be executed somehow at one point or another, right? And since they'll be executed, if I patch it with OXCC and I hook up a kernel debugger to it, and the exploit is successful, my kernel debugger should break in because CC is an int3, right? So this is how I went about it, and this is how I thought how this process. I didn't know it was going to work or not. So I went out and tried. It doesn't hurt, right? So this, the byte pattern I just show you is that. Like, it's like push, call plus 5, pop. This is pretty standard shellcode, right? But at the end, you see like exchange, EX, and ESP in a ret. It's kind of like ROP style, but I'm like, what the fuck, dude, ROP? And usually people don't use ROP stuff in kernel, or they use like in user mode. This is kind of weird. But anyway, so remind me to talk about the shellcode later, because it's actually pretty interesting. Like, the attacker may generate this code using some type of code transformation tool. So reminding me to talk about it later. But anyway, so when I listened to yep, it looks like real code to me. So I patched one of it to CC, and sure enough, it led me in the right direction. I patched a whole bunch of the bytes to CC, hooked up a kernel debugger, ran it, boom. The kernel debugger broke in, and I got a nice stack trace. And from there on, I literally sent the email when I got the stack trace. Holy crap, man! This is a breakthrough. I knew I was getting close. So I sent the stack trace to the team at like fucking like 1 a.m. and I went to sleep. Next morning, we came in, and with the stack trace, we were able to figure out what the bug was. So the bug is this: Windows allows users to load different keyboard layouts. Like, for example, if you're in China or whatever, in the US, the keyboard layouts are different. You can load them. Keyboard layouts are loaded on Windows Vista and higher. Keyboard layouts are loaded from the system directory only. So you can't, only admins can write there. But on Windows XP, it can be loaded from anywhere. That restriction is not there. So in kernel mode, what happens is like inside the function that loads a keyboard layout file, there's an integer that's read from the layout file. And this integer is used to index into an array of function pointers. And then the index is not properly validated, so basically the attacker can control this. They can basically get the kernel to call anywhere they want, right? But what the fuck, you can control the call what you want, but you need to know, like, you need to have memory allocated at the destination that you're going to call at first, right? So what the attackers did was, it's actually really smart. So the ANL SVK proc, that's actually the array of function pointers, right? And you see there are 3 function pointers there, like the top 3. WinRUK, KBDNS, blah, blah, blah. But then you see immediately a few bytes after that, you see the 60, 63, 62, 61, and 006E. So in Windows, the OX7, FFFF, and below is from in user mode. Anything higher than that is kernel mode. So what the attackers did was they search for, once they find the base address of this function, the array of function pointers, they start scanning down from there and to figure out where the next D word that is within the user mode range. So they found like 60, 63, 60, 61. Then they allocate memory at that exact address, and then they put code there. And then they change index so that the index will be 0, 1, 2, 3, 4, 5. The index will be 5. The kernel will call that function directly. And that's it. Now, one thing is that at this point, I should have realized that since I've analyzed a whole bunch of these Win3k.sys exploits, and every single time people need to map the null page, so they use NT-virtual allocate, I should have spotted that immediately. I should have set a breakpoint there and you see what's being written there. But at the time, I guess when you're under a lot of stress, you don't think through all the different options right away. But thank God, the previous OXCC trick works. So, but anyways, so that's how the exploit works. So from the attacker's perspective is, the task scheduler is only used if you're on Vista and higher. This vuln is only used if you're on Windows XP or below. Okay, and the exploiting the keyboard layout issue is actually pretty easy, right? I mean, I told you once you know what the details of the vuln is. I mean, it's like little kids can do this. My mom can do this. It's actually very easy. And then another thing is the attackers, the people who wrote this, their target environment must be somewhat diverse. It must have like XP and Windows Vista and higher. So they probably want to target everybody. So anyway, that's what I got out of it. All right, so of course, once we figured that part, I was like, oh man, this is like great. I found this. So I felt pretty good. So we found 3 vulns so far. And like, crap, like how can there be more? The ironic thing is, like, the guy who sits across from me, he told me, oh man, Bruce, keep on looking. There could be more in there. I told him, oh dude, like, quit joking around. Anyways, one day, Kaspersky sends us an email. It's like, hey dude, we saw some traffic. That's some weird like RPC traffic. Like, do you guys see this? Can you take a look into it? It's like, no, because I don't run malware on the network and stuff. Because I run a VM, right, but I don't usually care about like network connectivity. I don't usually care about that stuff. And so I said, no, I don't know about this. So we said, okay, well, let me take a look at this. So what I did was, I just set up 2 VMs and then had them connect to each other, and I ran Stuxnet on one of them. And I went to lunch. And then I came back and I discovered, fuck, dude, the other machine got infected. It's like, what the fuck, how's it going? This is weird, right? It's like one after another. Anyway, so this one is like, so this one at least, there's no stack trace or whatever, but I have packet trace. So when the packet trace, I was able to figure out what was going on. I saw that it was enumerating printer shares, as connecting to the printer share using a guest account, and then it's sending like write data to file or some crap like that. And it sends like an exe over in a MOV file. So I looked at the RPC routines that was used, and I was like, yep, this is in the spooler code, and the spooler is creating a file. But this, knowing this doesn't actually help at all, because this didn't make any fucking sense. Typically, the spooler needs to impersonate the user who's connected to it before it performs an operation, right? Because then it doesn't make sense for you to spooler. You gotta remember, spooler runs as like system, so it's like highest privilege. So, and I was like, I've worked on spooler case before, and like this logic does not make sense to me. How the hell is this happening? The file creation should have failed because guest accounts don't have privilege to create files in System32. So what we did at this time, so we added the printer team. Once we found out this is related to printer, we added the printer team. We figured this out, and it turns out that there's 2 special cases. The 2 special cases. One is that if it's a guest account and you connect into the network printer, then the system will impersonate itself, which is like system, and it will do the stuff for you. Or if the shared printer is one of some list of like 15 printers or something like that. And I'm like, what the fuck? So there's this comment on top that says, oh yeah, we have to do this because on Windows XP, the guest account doesn't have privilege to do X, Y, Z, and therefore we have to use system to do it. Yeah. So anyway, so we of course, once we figured this out, it took like 5 minutes. So the guy from the printer team, the guy literally had a fix within 5 minutes. Like, dude, Bruce, wait for I'm writing the fix right now, and I'm building the package. Like really fast. So anyways, but of course the fix was his initial fix only fixed one part. It wasn't a complete fix. Later on, we involved more people, and we found out that we had to fix other places. But yeah, so that's how we found the spool issue, thanks to Kaspersky. So the root cause is that, yeah, I just explained to you, spooler basically you can share a printer if you allow a guest account. Guest accounts can connect to it, and then tell the spool, once it's connected, tell the spooler, hey, print this data to a file for me, and you specify the path, and then you send the file. And that's pretty much it. Now, but the cool thing is that this vuln only allows you to write a file anywhere you want. It doesn't allow you to execute the file. So that's where the MOV file comes in. This is like pretty creative because I didn't know about this. The MOV file is actually like kind of like compile script almost. And they wrote the MOV file in system32/wbem/MOV. And I'm like, what the fuck is special about why this directory? It turns out Windows has a thread that continues watching this particular directory for new files being dropped in there. Once a new file is being dropped in, it picks it up and it runs it. Now you can remember, right? So people were thinking, okay, well, like, is that like a vuln? Like, no, it's not a vuln because like you need admin access to write files to this place anyways. And it's not an exe that you run. It's like some compile stuff. But anyways, so what they did was they wrote a script to run the exe file they just wrote, and that's it. Yeah. Yeah, I'm not going to talk about the details how we fix the principle because it's really complicated. But anyways, from the attacker perspective, so this vuln only exists if the printer server was allowing anonymous connections. So the target network that they were going after must have had servers with this configuration. That's why, I mean, otherwise there's no point, right? And this is the way Stuxnet spreads on the network. Once it's on the computer, it scans, enumerates all the shares around it, and then if it is connected, it uses exploit. So the attackers must have wanted like large-scale infections. You know, I'm not sure why they want to do this, but that's what I think. That's at least my hypothesis of it. And the attack had good tricks too. Like for example, I didn't know about this moth trick, but they did. So the lessons I learned from this is doing like a thorough job is like really hard. It requires a lot of time, and in real life, when you're being asked questions like every few hours, it's pretty stressful, and like you don't have time to go line by line and explain it, right? Especially it's black box and you don't know what you're gonna find, you don't know what you're looking at. So you gotta find a balance between there. And then so in my case, I learned the mistake from that was like I took the old school approach, which is literally starting from main and tracing down. That's like bad news. Don't do that. Only do that when you have time. But yeah. And the other one is like the ability to figure out important facts and then putting them together to see a bigger picture is really important. Like for example, in the WinThrough assist case, like I figured all this stuff out, but I couldn't quite figure out how they all fit together until like towards the end. So if you figure them out early, you can at least get some clues, and it's easier for you to debug. And the other one is like work with other people. For example, Arthur, he doesn't like reverse engineer stuff, but he has good ideas, right? So I should have used, listened to him when I should not have doubted him when. I should have told him that process monitor was useless for reverse engineering. So that was like bad of me. But anyways, yeah, work with other people, and also like one person, you're not gonna know everything. Like you don't know how spooler works in and out. You have to talk to the guys who work on this every day, so they can explain stuff to you. Like you might be able to know one aspect of it, but there may be other aspects that you don't understand that may affect the end result. And the other one, okay, about the attackers. That's all the vulns. After that. I spent time decompiling the rootkit, and Rolf did the DL loading part. And we spent a lot of time analyzing the. Since now we're pretty confident that we found all the vulns. I mean, literally, manager came and asked me, Bruce, are you 100% sure that there's nothing else in here? And I said, yes, I am sure. And that was, thank God, I was right. But anyways, yeah. So after that, we had some free time, so I decided to take a look at this a little bit more. And based on like the way the code is written, I could tell that the malware components were written by different people. Like for example, the exploit were written by different people, and the rootkits were written by. The rootkits basically what it does. One is to hide files. The other one is to inject code into like, user land. That's the SCADA infection stuff. So they were written by different people, and like the driver was built from probably like a removable media, because like when you create Windows drivers. And you build it with the Windows driver development kit, the build environment, it'll automatically embed the full path to your project in there. So I think the path they had was like B:/WAC guava, something like that. So B drive is usually like removable, like probably like a floppy disk or something like that. I don't know. But anyways, the attackers were definitely aiming for 100% reliability and high impact. All the exploits I just explained to you will run like 100% with 100% reliability. Like there's no crashing. Even the kernel exploits, right? So yeah, they really wanted reliability. Apparently, they didn't want the computers to crash, or they didn't want people to notice. Decompilation. I don't know if I have enough time to talk about this. I didn't actually prepare the slides because it's like really involved. There are different tricks when we. Okay. Wait, what does that mean? I have enough time? Not enough time? Okay. Well, I mean, it's not gonna be much. I'm not gonna talk about. I didn't. So I didn't put the details here because the topics was probably going to be like, once when I wrote the slides, I realized that the whole process of decompiling this back to C code will probably require another talk, so which Rolf and I will probably do at one point or another. So there are the different tricks when you decompile. So most of the time, you don't need to decompile stuff, right? You only need to do that if it's like, if you want to feel good or you want to test your skills. Before I've decompiled code before, but just like one function, like one or two functions at all. But I've never done like full program decompilation before. And this one seems like the target was good enough for me to decompile, so I went ahead and did it. And it's a Windows driver. and like the different tricks you have to use. Like for example, like there are a lot of compile optimization that you have to be aware of and figure out, okay, to go from the disassembly code back to the like the source code, blah blah blah. So maybe we'll talk about that another